welcome you in the lecture series of quantum computing. This is another lecture on Introduction to Quantum Mechanics. In this lecture, we will discuss expectation value, variance, eigenstate, eigenvalues, and eigenfunction. Let the quantum state psi is alpha cat 0 plus beta cat 1. Here cat 0 and cat 1 are the quantum basis, and the quantum basis cat 0 can be written as in column matrix as 1 0, and quantum basis 1 it is written in column vector as 1 0. Now the probability amplitude of finding the system in state 1 after making the measurement of psi, it is beta, and this can be calculated by taking the inner product of quantum basis 1 and quantum system psi. So the inner product is the bracket notation, and it will be bra 1, and psi is alpha cat 0 plus beta cat 1, and here I can write alpha inner product of 1 0 plus beta inner product of 1 and 1. The quantum bases are orthonormal, so it will be equal to 0, and the inner product of 1 and 1 it is equal to 1. So it is beta. So the probability amplitude of finding the system in state 1 after making the measurement or on quantum state psi, it is beta. And the square of the probability amplitude is the probability of finding system. So the probability of finding system in state 1, it is beta square, and it can be written as mod square of the inner product 1 and psi. If quantum state psi is the wave function of time as psi xt, then the probability of this function psi t, it is equal to the mod square of the wave function psi xt. And if we make a large number of independent measurements of the position or displacement of identical quantum system, then the result of these measurement may be quite different. Then the mean of these measurement can be described using the probability theory. And with the probability theory, expected value of x, it is integration x f x dx. So the expected value of the position x, it is integration the position operator x and the probability, and the probability will be the mod square of the function, wave function psi square and dx. So the expected value of position, it can be written as integration the position operator conjugate of wave function psi xt, wave function psi xt dx. And if the wave function psi xt is normalized, we can say integration of conjugate psi xt and psi xt dx is equal to 1. Here the position operator x is basically the Hermitian operator representing an observable. So we have seen the expected value of operator x, it is integration the complex conjugate of wave function psi xt, position operator, and wave function psi xt dx. And this can be written as the inner product of operator and the wave function psi as here. And this represents the expectation value of the position operator x in the quantum state psi. So various measurements of the position x are scattered around this mean value or expected value, and the degree of the scatter is termed as the variance, and the variance is given as mean square value minus whole square of the mean value, where sigma x is the standard deviation or scatter. This is a type of inner product. It is mathematically a sandwiched inner product, an inner product with an operator in the middle. It is a linear product between bra psi and x cat psi. It is a scalar representing a measurable quantity. Let us consider one example. let psi is equal to 1i and operator A is equal to 2003. This is a square matrix. We want to compute psi A psi, means the expectation value of A in the quantum state psi. So here this is basically inner product of bra psi and A cat psi. So first we measure this A cat psi. So A cat psi, it is equal to 2003 and cat psi is 1i. So it is equal to 2 3i. And you know bra psi, it is the conjugate transpose matrix, or you can say dagger of cat psi. So it will be equal to the row matrix 1 minus I. So now the inner product of bra psi and A cat psi is equal to 1 minus I and 2 3I. So it will be equal to 2 minus 3I square. 2 plus 3, it is 5. This is scalar, and this scalar 5 is the expected value of the observable when the system is in quantum state psi. So you know the expected value A, it can be written as the sandwiched inner product of A and psi. So this scalar value is the expected value of the operator A. Now consider another example. If operator A is the poly Z matrix and psi quantum state is 1 by under root 2 cat 0 plus cat 1. You know the poly Z matrix sigma Z, it is 1 0 0 minus 1. This is operator A, and psi can be written as in column matrix as 1 by under root 2 1 1. You have to compute here the expected value of A for sandwiched inner product psi and A. So first of all we will consider A cat psi, and it is equal to 1 0 0 minus 1, and cat psi is 1 by under root 2 1 1, and it will be equal to 1 by under root 2. The product of this and this, it will be 1 and minus 1. Now the product of bra psi and A cat psi. So bra psi is will be the row matrix, and it is 1 by under root 2 1 1 into 1 by under root 2 1 1. So you will get here it is 1 by 2 1 minus 1, and it is 0. So the expected value of the observable or physical quantity represented by the operator A when the system is in the quantum state psi 1 by under root 2 cat 0 plus cat 1. In this case, the expected value of the observable is 0. Here A is basically the Hermitian operator representing an observable. Now eigenvalue and eigenvectors. Eigenvector are the direction that remains unchanged during the transformation, even if they get longer or shorter. If A is a matrix and we apply this operator or matrix on the eigenvector, we will get the same eigenvector with the eigenvalue lambda. So AV is equal to lambda V. The eigenvalues are the numbers that indicate how much something is stretched or shrink during the transformation. Eigenvectors are vectors that are associated with the matrix or operator such that when the matrix multiply the eigenvector, as here A into V, the resulting vector is a scalar multiply of the eigenvector. This scalar is the eigenvalue. Eigenvectors are also called the characteristic vectors and can only be found for square matrix or operators. Eigenvalues are the scalar values associated with the eigenvectors in the linear transformation. The word eigen is of the German origin, which means characteristic. These ideas are important in many areas of mathematics and engineering, including studying how systems stay stable, and understanding quantum physics or mechanics. They are also important in fields like machine learning, where they help to simplify complex data by reducing its dimensions. There may be a certain quantum state psi such that the action of an operator results in a linear multiplication of the quantum state psi. So, when this operator O is applied on the quantum state psi, it will be equal to A, and the quantum state psi. Here, this is the operator or matrix, and this one A is the eigenvalue. Here psi is the eigenket of operator O or eigenvector. The wave function psi is the eigenstate or eigenvector. When we project this ket into an observable basis, psi is known as the eigenfunction. The value A is the eigenvalue here, and this kind of equations are eigenvalue equations. The set of eigenvalues of an operator are known as the spectrum. The eigenvectors correspond to the distinct eigenvalues form a subspace known as the eigenspace. For example, time independent Schrodinger equation is Hermitian operator H, quantum state psi, it is equal to E, the quantum state psi. This is an example of eigenvalue equation. Here H is the Hamiltonian operator of the eigenfunction psi, and E is the eigenvalue. In this equation, Hamiltonian operators operates upon a wave function psi to produce energy times the wave function. That operator O is a Hermitian operator corresponds to the physical observable O, and psi A is the eigenstate and A is the eigenvalue. Now the expectation value of O is as integration the operator O and probability, and you know it will be the mod square of the wave function and dx, and I can write it as integration complex conjugate psi A operator O psi A dx, and if psi is normalized, then integration minus infinite to infinite complex conjugate psi A dx, it is equal to 1. So here it will be A psi A complex conjugate and psi A dx, and it is equal to 1. So it is A. So here we can write the eigenvalue equation as operator O psi, it is equal to A eigenvector psi. And you know mean square value of the operator, it will be minus infinite to infinite integration complex conjugate psi A, the operator O square psi A dx, and it is equal to A square integration psi A dx, and it is equal to 1, it is A square. So now variance, it will be mean square minus whole square of the mean value of the operator, and it is A square minus A square 0. Since the variance is 0 here, we can deterministically measure the quantity. It is also implied that the eigenstate psi A is uniquely attached to the eigenvalue A for the Hermitian operator O. When two eigenstates psi A and phi A of the same Hermitian operator O correspond to the same eigenvalue A, then the eigenstates are said to be degenerate. Besides this, the eigenstate psi A and phi A of the Hermitian operator O correspond to different eigenvalues A1 and A2. Then the eigenstates are said to be orthogonal in that case. And these are orthogonal, we can write integration psi A complex conjugate and phi A dx, it will be equal to 0 if it is orthogonal. Here, if I consider two eigen functions psi ix and psi jx of Hermitian operator O with eigenvalues ai and aj, if these ai not equal to aj, these eigenvalues are not equal, then These eigenstates or eigenfunction psi ix and psi jx are orthogonal. So in that case, integration psi I conjugate x minus psi, then integration conjugate psi ix into psi jx dx is equal to 0. If psi x is the linear combination of psi 1x, psi 2x, so I can write psi x is equal to a1 psi 1x plus a2 psi 2x and so on. And this property is generalized as the quantum superposition principle. So here psi x can be written as the summation of the quantum basis psi I x and weighted with the probability amplitude AI, or you can say eigenvalues AI, where sum of the square of the probability amplitude, it will be equal to 1. Again, if we consider the Schrodinger equation, time independent Schrodinger equation, h wave function psi is equal to e wave function psi. H is the Hamiltonian operator, e is the eigenvalue, and psi is the eigenfunction. The term eigenvalue is used to designate the value of the measurable quantity associated with the wave function. That is, if I want to measure the energy of the particle, we have to operate Hamiltonian operator on wave function. The meaning of eigenvalue and eigenvectors or eigenstate depends on what operator and what observables you are considering. If operator is Hamiltonian, then the eigenvalue you get will be the energy of the system, and eigenvector tells you its state. Like Schrodinger equation, another example is the momentum operator. Then it will be momentum operator P and wave function psi x. It will be equal to P psi x. And the momentum operator P, it will be equal to minus I h bar d by dx. So I can write here minus I h bar d by dx psi x, it is equal to p psi x. Here psi x wave function, it can be represented as a, amplitude a is to the power I p x by h bar. Wave function, plane wave or eigenstate. So from here I can write d by dx psi x, it is equal to I p by h bar psi x. Here p is the eigenvalue, is the momentum of the particle. So if operator is momentum operator p, then the eigenvalue will be the momentum of the particle of the system. Now here is one example. Prove that the eigenvalues of the Hermitian operator are real. We know for Hermitian operator, integration psi j x operator o psi I x dx, it will be equal to psi I x into operator o psi j x and conjugate dx. And if psi I x is equal to psi j x is equal to psi, then we get a is equal to a complex conjugate, which is not possible unless A is real. So we can say the eigenvalues of a Hermitian operator are real. Now, characteristic polynomial. The characteristic polynomial of a square matrix is polynomial whose roots are the eigenvalues of the square matrix. For a square matrix A, we say that lambda is its eigenvalue if there exists a non-zero vector V known as eigenvector such that AV is equal to lambda V. So here this is operator A and lambda is the eigenvalue and V is the eigenstate or eigenvector. Or here this I can write as A minus lambda I V is equal to 0. This is characteristic equation, and the eigenvalue of A are the roots of determinant A minus lambda I, which is polynomial in lambda. Spectral decomposition. In quantum mechanics, every physical quantity, position, spin, energy is represented by a matrix or operator A. When you measure it, you do not get just any number. You only get one of its eigenvalues. After the measurement, the system jumps into the corresponding eigenvector or eigenstate. The spectral decomposition is just a recipe for writing an Hermitian operator in terms of its eigenvalues and eigenvectors. So if there is an operator A, it can be written as the summation of eigenvalues multiplied by the outer product of the eigenstate. Here lambda I is the possible outcome or eigenvalues of the measurement. This is the reading on the device, and cat Vi is the state of the system collapse into if that outcome happens. And this outer product of Vi, state Vi, is the operator on the eigenstate Vi, or you can say the outer product. So spectral decomposition is simply writing an operator as the sum of the eigenvalues and projector. In quantum mechanics, it directly encodes measurement outcomes and probabilities. Think of spectral decomposition like splitting light with a prism. The operator A is like a white light. The eigenvalues are the colors you can actually see, and the projector, this outer product of Vi, are the filter that pick out each color. Now, if we have a system in state psi, when we measure this operator A, the probability of getting lambda I, it will be equal to the inner product of the actual state and the eigenstate. So this will be the inner product of Vi and psi mod square. So probability of getting the eigenvalue lambda I, it will be the mod square of the inner product of actual state and the eigenstate Vi. And after the measurement, the state collapse to cat Vi. If you repeat the measurement many times or identically repeated system, the average value of A, it will be the sandwiched inner product of A and psi, and this is equal to the sum of eigenvalues weighted with the probability of that eigenvalue. Now consider one example. Find the eigenvalues and eigenvector of the polymatrix X. You know the polymatrix X is the matrix with element 0, 1, 1, 0. Now the characteristic equation we can write x minus lambda iv is equal to 0. You know this is the characteristic equation. So the determinant of this characteristic equation, it is x minus lambda I. You can write it will be matrix 0, 1, 1, 0 minus lambda I. It is lambda 0, 0 lambda. So we will get the determinant minus lambda 1, 1 and minus lambda. So we will get the multiplication of this minus multiplication of this. We will get lambda square minus 1, or you can write it as lambda plus 1 and lambda minus 1. So we are having two values of lambda. These are plus 1 and minus 1. These are the eigenvalues. Now to find the eigenvector corresponding to eigenvalue lambda plus 1. So for lambda plus 1, you know x minus lambda I from the previous slide, it is minus lambda 1, 1 minus lambda. And if the lambda is plus 1, so this will be equal to minus 1, 1, 1 minus 1. So x minus lambda into v, this one is x minus lambda, and eigenvector v is v1, v2, it is equal to 0, 0. So from here we can have minus v1 plus v2 is equal to 0, and v1 minus v2 is equal to 0. And from these two equations we get v1 is equal to 1 and v2 is equal to 1. So the eigenvector is 1, 1, and the norm of this eigenvector, it will be under root 1 square plus 1 square. This is under root 2. So the normalized eigenvector 1 by under root 2 cat 0 plus cat 1, or I can write this is cat plus the diagonal basis or x basis. Similarly, with eigenvalue lambda minus 1, the normalized eigenvector will be 1 by under root 2, 1 minus 1. See how x minus lambda I, v is equal to 0, and when And you know x minus lambda I, it was minus lambda 1, 1 minus lambda. When lambda is equal to minus 1, so it will be 1, 1, 1, 1. So here this one will be 1, 1, 1, 1 and V1, V2. It will be 0. So from here V1 plus V2 is equal to 0. V1 plus V2 is equal to 0. So from here we will get V1 is equal to 1 and V2 is equal to minus 1. So the eigenvector, it will be 1 minus 1, and norm of this 1 and minus 1, it will be 1 square plus 1 square under root, this is under root 2. So the normalized eigenvector, it will be 1 by under root 2, 1 minus 1, or I can write 1 by under root 2 cat 0 minus cat 1, or I can write it as cat minus. So here we have seen the eigenvalues are lambda 1 is equal to plus 1 and lambda 2 is equal to minus 1. And the eigenvectors are V1, it was 1 by under root 2, 1, 1, or you can say plus. And eigenvector V2 corresponding to eigenvalue minus 1, it is 1 by under root 2, 1 minus 1, or you can say cat minus. Now the spectral decomposition of X, polymatrix X, spectral decomposition is basically the summation of eigenvalues multiplied by the projector V1, or outer product of eigenvector V1. So now the spectral decomposition of X, it will be the summation of eigenvalues lambda I and the outer product or projector of Vi. So it will be equal to the eigenvalue 1 and corresponding eigenvector is plus. So the projector of eigenstate plus eigenvalue minus and corresponding projector of eigenvector minus. And this outer product cat plus bra plus, and it will be equal to 1 by under root 2 cat 1 is 1 1 and 1 by under root 2 bra plus is row matrix 1 1, and it will be equal to 1 by 2 1 1 1 1. Similarly, the projector of minus or outer product of cat minus, it is cat minus bra minus, and it will be equal to 1 by under root 2 1 minus 1 into 1 by under root 2 1 minus 1. So this is equal to 1 by 2 and matrix 1 minus 1 minus 1 1. So the poly X matrix, which is 0 1 1 0, in spectral decomposition, it can be written as eigenvalue 1 into projector of eigenvector plus eigenvalue minus 1 into projector of eigenvector minus, or I can write it as 1 into 1 by 2, the matrix 1 1 1 1, plus minus 1 1 by 2 1 minus 1 minus 1 1. So poly X matrix can be expressed in terms of its eigenvalues plus 1 minus 1 and corresponding projectors onto eigenvector cat plus and cat minus. Now for state cat psi, the probability of getting the eigenvalue plus 1, it is basically the mod square of the inner product of actual state and the eigenstate, and the corresponding eigenstate is plus. So this is the mod square of the inner product of plus and psi, that it is alpha square. This is probability of getting the eigenvalue plus 1. Similarly, the probability of getting eigenvalue minus, it is the mod square of the inner product minus and psi, it is beta square, mod beta square. So here the quantum state psi, it can be written as the superposition of eigenstate of poly X that are cat plus and cat minus. So psi is alpha cat plus beta cat minus, and probability of getting cat plus, it is alpha square, or you can say the mod square of the inner product of eigenstate plus and quantum state, actual quantum state psi. And the probability of getting minus, it is mod square of the inner product of minus and actual state psi. The eigenvalue plus 1 is the measurement result, and the eigenvector cat plus is the state of the system ends up in after you see plus 1. And the probability of collapsing into state cat plus is mod square of the inner product of quantum state plus and quantum state psi. Now, if I consider psi is 1 0, or you can say psi is cat 0. So now probability of getting eigenvalue plus, it is the inner product of eigenstate plus and actual state psi mod square, or you can say it is plus and 0, it is 1 by under root 2, 1 1 and cat 0, it is 1 0 mod square. So you will get here multiplication of these two matrices. You will get 1 by under root 2 into 1 and mod square. So you will get 1 by 2. Similarly, probability of getting the eigenvalue minus 1, it is the mod square of the inner product of minus eigenstate minus and quantum state psi, or I can write minus 0. It will be equal to mod square and root 1 by and root 2 1 1 and cat 0 is 1 0. This is mod square and it will be 1 by 2. So this quantum state psi, it can be written as 1 by under root 2 quantum state plus 1 by under root 2 quantum state minus. So measuring x in state 0, you will get the state 0, it can be written as the superposition of the x basis, means cat x plus cat minus. Or you can say the state 0 can be written as a superposition of the eigenstate of poly x. Similarly, computational basis of state 1 means when psi is equal to 0, 1 or quantum state cat 1, then the state 1, it can be written as the superposition of the eigenstate of poly x, means it is 1 by under root 2 cat plus minus 1 by under root 2 cat minus, or I can write 1 by under root 2 cat 0 minus cat 1. And in terms of computational basis, this cat plus is 1 by under root 2 cat 0 plus cat 1, and minus cat minus, it is basically in computational basis 1 by under root 2 cat 0 minus cat 1. So when we measure poly x and we have the quantum state psi is equal to 0, then the quantum state psi can be written as the superposition of the eigenstate of poly matrix X, means cat plus and cat minus. In quantum computing, we often switch between different bases Z, X, Y. A spectral decomposition tells you what the natural basis of the operator is. Means if you are having the X basis cat plus, it is 1 by under root 2 computational basis cat 0 plus 1 by under root 2 cat 1. Here 1 and 0 are the natural basis. Measuring poly x operator, like in this previous example, in its eigenbasis cat plus cat minus, that is x basis. This means x is equivalent to measuring in the state cat plus cat minus basis of the diagonal basis. Means here poly x operator is basically 0 1 1 0. This is not diagonal. This poly x matrix with the computational basis cat 0 and cat 1. And here this is not diagonal, it swaps 0 to 1 and 1 to 0. Measuring of poly x in the x basis, then x will be 1 0 0 1, and its computational basis, measuring basis of poly x is plus and minus. And here measuring of poly x in x basis, we can see changes the eigenbasis of x marks X diagonal with its eigenvalues on the diagonal. So here in the diagonal these are the eigenvalues, and we have changed, this is not diagonal, but here the measuring of poly X in the X basis, it is diagonal, and the diagonal elements are the eigenvalues. So here poly X having the eigenstate ket plus ket minus. Similarly, you can see the poly Z has the eigenstate ket 0 and ket 1. Measuring poly X in state psi is different from the poly X applied to the state psi. Means if I apply the poly matrix on quantum state 0, you will get state 1, and if I apply the poly X on quantum state 1, you will get 0. So 1 is quantum state 1 is changed to 0 and 0 changed to 1. Now if the state 0 and then measure the poly X gate, we will get plus for eigenvalue plus qubit collapse to ket plus. This means 1 by under root 2 ket 0 plus ket 1, and when the eigenvalue minus, then the eigen state is minus 1 by under root 2 ket 0 minus ket 1, and each eigenvalues are with probability 1 by 2, as you have seen in the previous slides. And in previous lecture we have learned that how we can decompose the poly X matrix in the outer product form. We can write poly X matrix, the elements are 0 1 1 0, and the quantum bases are ket 0 ket 1. Here it is in bra form, bra 0 bra 1. Now this in outer product form, it can be written as bra change to ket and ket change to bra, ket 0 bra 1 plus ket 1 bra 0. So this poly X matrix in outer product form, it is written as, we have taken the example of poly X matrix. We can take poly Y and poly Z matrix. With poly Y matrix, the eigenvalues will be plus 1 minus 1, same as in poly X matrix, but the eigenvectors are 1 by under root 2 1 I and 1 by under root 2 1 minus I. This means here the eigenvectors are ket plus and ket minus, and in this poly Y matrix the eigenvectors are ket I and minus ket I. In if we consider the poly Z matrix, the eigenvalues are same plus 1 minus 1, but the eigenvectors will be ket 0 ket 1. You can do the calculation as we have done for the poly X matrix, and you can see in the outer product form, poly X matrix is written as the outer product of ket 0 ket 1 plus the outer product of ket 1 ket 0. Similarly, the poly Y matrix in outer product form, it is written as I into outer product of 1 0 minus outer product of 0 1. And poly Z matrix in outer product form, it can be written as outer product of 0 0 minus outer product of 1 1. This is the end of this lecture. In the next lecture, we will discuss about the tensor product. Till then, thank you.